Hi guys, this is Aditya, and now we are going to solve problem of the day on GHG. So let's see the problem. What is that problem? So problem is that a number of good components. Okay, so we have to uh, solve this question. That is number of good components. So let's read the question. Given an undirected graph with v vertices. Okay, we have v vertices. Number from 1 to v. Okay, and e edges. Okay, so find the number of good components in the graph. Okay, so we have to find the good component of the graph in the graph. So what is the good what is the definition of good component of the graph? Let's see. A component of the graph is good if and only if the component is fully connected. That means the components should be fully connected. So we can say, like, we have a different components, so those components have fully connected is my answer, or it's my good component. Okay, so one note is here: a fully connected component is a subgraph of a given graph such that there an edge between every pair of vertex in the component. The given graph can be a disconnected graph. ओके ठीक है, ये समझने के बाद तो आगे समझते हैं. लेट्स सी दैट एग्जांपल नंबर 2. ओके, so we can say that say this 3 4 5 is a fully connected component graph. Why? Because 4 is connected to 3, 4 is connected to 5. That means in this component the number of vertices 3, so each vertex is connected with every vertices. Okay, each vertex should be paired with other vertex and all other vertex, not single. All the vertex which present in same component should be pair or should be connected. So 3 is connected to 4, 3 is connected to 5. But in this component, we can see that one is connected to 2, but one is not connected with 7. So we can say that this is not a good component. And see, because in this component there is only one vertex, so we can say that 6 is my good component. So we there is a very basic or very simple question. Just you have to know one thing. The thing is that the if you know about the complete graph, then you will get the answer very quickly. How can we see that? Okay, so do you know what is complete graph? So let me make a graph. This is a one node. This is another node. I have 4 vertex. Okay, vertex 1, vertex 2, vertex 3, and vertex 4. So complete the definition of complete graph is all the edges, all the vertices should be connected to each other. That means 4 should be connected to 3, 4 should be connected to 2, 4 should be connected to 1. Okay. Similarly, 1 should be connected to 2, 1 should be connected to 3, and 1 should be connected to 4. So this is undirected graph. So if 4 is connected to 1, so 1 also connected to 4. Similarly, for 2, 2 is connected to 1, 2 connected to 4, 2 connected to 3. And for 3, 3 is connected to 4, 3 is connected to 1, 3 is connected to 2. So can we say this is my good component? Just think. Yeah, definitely. This is my good component. Okay. And we can see that every vertex is connected with every other vertex. Okay, so one thing we determine here, that uh, the number of edges. How many number of edges? That is 1, 2, 3, 4, 5, 6. That is 6. So we know that a formula that calculate the number of edges in complete graph, that is n into n minus 1 and divide by 2. Okay, so here what is n? N is my vertex, number of vertex. So here what is the number of vertex? Is 4. So 4 into 4 minus 1, that is 3, and divided by 2. So 2 is cancelled 4 by 2, and 2 into 3, we can see that 6 is my number of edges. Okay, so we have to remember this formula, because we are using this formula and we will use later. So this is the concept behind the complete graph. Okay, so we should know about that. Okay, this is concept. Okay, and this formula is very important because we will use further. Okay, now next thing is that let me erase that. Now next thing is that this is my second example. That is, this is one of my component. Okay, this is another one, and this is another one. Okay, we can say this is 1, this is 2, 3, 4, 5, 6, and 7. Okay, so what I'll do, we everyone know about DFS search. So we will do a DFS search. Okay, take a vector which is store the visited, it is visited or not, and this vector will help to decide that is visited or not. Okay, this is one, this is second, this is third, this is fourth, this is fifth, and this is sixth, and one more vertex we have, that is 7. Okay, so firstly we start from 1, we call it DFS 1 from the function, and it will go first of all it call 1, then it will go to 2, then it will go to 3, then it will go to 1. So it is visited, so it is returned back, and we are normally here is doing DFS search. Okay, so during the DFS search we have to maintain two things. We create a two variable. One is v, v stands for vertex, and another is e, e stands for edge. Okay, two things we have to determine. Okay, so if I will call DFS search for 1, so I will increment my vertex v plus plus, because I encounter one vertex, and the number of edges is connected with this, how much, that is, if we have adjacency list, that means adj of v dot size, you know, that all the vertices is connected with different vertices. So I will add into the edges. Okay, so we will add into the edges, or we are adding here into the edges. Okay, so first thing we increment the vertices, and second thing we will add the number of edges. Okay, so after doing that, I will go to 3, then I will increment the vertices, that my vertices will be 2, and the uh, number of edges is connected with that, that is 3, sorry, 2. Okay, so 2, so 2, 2 plus now becomes 4, then it will go to 2, so vertices increase by 3, and it will connected by 2, so it will become 6. Okay, so for this graph, just understand, uh, for this graph, okay, for this graph, so we have vertices, how many, that is 3, we calculated, and edges is 6. Okay, so can we say this is my complete graph, because 1 is connected to 2, 2 is connected to 3, 3 is connected to 2. Okay, this is my complete graph, can we say? So number of edges we have discussed sometime later, or we have discussed just 2 to 3 minutes ago. The number of edges will be n cross n minus 1 divided by 2. You know that? Okay, so that means this is my 3 vertex. We have 3 vertex, so 3 into 3, because we have calculated this one, 3, 3 minus 1 divided by 2. That means it will cancel by this one, and we have a 3 edges. But here you can see 6 edges. How? Look, 6 double is contributing here. That means 6 by 2 is my exact edges in the complete graph. How? Let's see. 2 is contributing 1 and 3. Okay, 3 is contributing 1 and 2, but I have already count 1. Okay, so this is my extra. Okay, and 1 is calculated, counted, uh, count to 2, but 2 already calculate this, so this is my another extra, and this will count again extra, so we have 3 extra. So you can see this, if 2 divided by 6, so we will get 3. That means 3 is my exact age, 1, 2, 3, and 3 is my extra age, so I will plus 3 or multiply with 2, we get extra age. That means connected in both ways, so we get 6. So 3 is my number of edges. We have vertices, we have edges, so edge, if so, we have vertices, we have edges. Okay, so we can say that if condition is that v is equal to e, that means my answer will be plus plus. Okay, That is a simple logic for that. So you can see there, you can see here, uh, this is for one component. So similarly, we know that how to calculate. I suppose that I assume that you already know how to calculate this component uh, graph in a graph in the graph. So you have to run this algorithm for every component, and you will get that that component will good or not. That is means this will the condition, or this will help you that find the component is good or not. Okay, not for counting the discomponent graph. For counting the discomponent graph, you have to use visited vector, and I think you have already know about that. So I am left this part. I left this part, and now we are going to code. So this is my question. Okay. So you can see that I am taking here two. This is my okay. First of all, this is my DFS, simple DFS. You know that. Okay. Uh, okay. And left this part. We don't need that because I'm trying another logic that logic did not work here. So that's why I apply different logic. I applied different logic. Okay. So you can see this is a normal leave these two lines. This is my DFS function. So this is my visited vector. This is I'm calling adjacent values. If it is not visited, then if it is not visited, then I will call the DFS call. I will call DFS. Okay. This is my adjacency vector. Okay. I will create. I am creating here adjacency vector. Here I am creating here adjacency vector, and this is my visited. Okay. So this is I'm calling 1 to n. This is my number of vertices, and if it is not visited, then I will call. Otherwise it is visited, that means we have already visited. Okay, so I will call here, and I will maintain two variable, that is vertex and edge. Vertex decide number of vertices, edge decide number of edges. Okay, so I will call DFS here. Okay, for first, so it will go and here count the vertex as same I explained there. I have explained there, and edges we will calculate adjacent node dot size. So we get edge, or we get vertex. We get edge of every node. Okay, total is from every node. Okay, after doing that, we get uh, we get the edge and vertices. Okay, so this is my edge. So I will divide. We have explained there. We have explained there that it will contribute a double the edges. That means a complete graph has is equal to n into n minus 1 divided by 2, where n is my vertex. So if age, which is calculated by my DFS function, and vertex, which this we will also calculate by DFS function, but my formula is saying that v cross v minus 1 divided by 2. If it is equal, then I will count. That means this is my good component or good graph. Okay, so I will increase the count, and after doing all that, all the components for all components, so I will count, increase, count plus plus, and return the count. Okay, so this is the solution, and that is easy to understand. That is nothing more than just DFS function. I think you know very well, and you have familiar with this uh, DFS function. If you are beginner, then you just need some time. After that you will be familiar, then you that is very easy for you. Okay, so just we compile and run. We are going to compile run, and you can see that that is one by one. And now I'm going to submit. Let's see. Yeah. Okay. Is it okay? So this is the solution. And what is the time complexity and express complexity? So time complexity, here I am initializing the vector which is O of n. So we can say O of n, that is number of vertices, and here we can see we are making adjacency vector, so adjacency list. So here it will take O of e. Okay, and here I'm running that the loop from 1 to n, and this is DFS function. So DFS call for those vertices which is not visited. That means it will approximately uh, the DFS, the time complexity of DFS, that means V plus E. Okay, so my overall time complexity will be V plus E. Okay, and what is the space complexity? So here I am using a visited vector. So O of n, and here is the adjacency list. I will making adjacency list. So in the worst case, I think it will be n square, or sorry, in V square. Okay, so space complexity, here I am writing that a space complexity is O of V square plus O of V. Okay, and time complexity is O of V. V is my vertices plus O of V plus E, or we can say O of V again V plus E. Okay, this is my time complexity. Okay, okay. Now I am explaining one more solution which I was solving starting. Starting I will solve. I was solving that method, but it will go to wrong, and then it was wrong. That was wrong. But let's see. This is that. Okay. So this is my solution. But I don't know why all the test cases has passed, but 4 test case has not passed. So uh, so you can see this. I'm just simply using digital vector, and here I'm not using the formula of completed graph. Just what I do, I will go at every edges, and and after the backtracking, during the backtracking, okay, during the backtracking, I will compute the size, and I will take that length, because if it is a good component graph, then I will explore all the nodes, and and count the length of that number of vertices. So I will count that 1 2 3. Okay, so during the backtracking, I will count that number of edges should be equal to the length minus yeah, length equal to length, but length might like in this way 1 2, this will not increase. Okay, so 3 should be equal to 2. Yeah, definitely it will equal to 2, and similarly for 2 and 1. But I don't know where is the problem, and 4 test case was not passed at that time. So you can see there, I submit this code and by this code and submit it. You can see that all the test cases passed, just 5 test case has not passed. Okay, so thank you. This is for today. And another thing, we are using a recursive stack, recursive space. So you can see the depth of the graph, which is the maximum height of the graph, or we can say depth of the graph. Okay. So this is for today. Uh, Thank you. We will see tomorrow.